Previously, when we've talked about the position of a particle, we've always described its position in terms of its x and y position. So when an object, let's say this object is moving in a circle, so maybe for example this is a car driving in a circle, I could, if I wanted to, describe the car's position right now based on its x position. I would just, figure out how many meters over we are in the x direction and how many meters I am in the y direction. I could give this coordinate as an xy coordinate. That's not going to be that useful as we move forward because, as you can see here, if I want to know where is the car on this circle, it's driving around in the circle, and I just want to know where is it on the circle. If someone's giving me XY coordinates, I'm going to have to pull out a calculator and draw a bunch of pictures and figure everything out. However, if I know the car's driving in a circle and I said something like the car's at 12 o'clock or 3 o'clock or 9 o'clock, or maybe this one here I describe as like the car's at roughly, let's say 1:30 or something. That gives you an instant image and an instant idea of where the car is on the circle. Okay, so that's what we're gonna attempt to have a new description of position that is not in terms of x and y variables. It's going to be similar to picturing that this is a clock face kind of, and saying something like the car is at the 1:30. Okay, but we're not going to quite do it in terms of a clock. So what we're going to do is we're going to make an angle theta, and that theta is going to be what we call the angular position. So the variable we're going to use for position when we're describing an object moving in a circle is going to be theta. And it's not just the normal position like an xy position, it's called an angular position. It's always defined with respect to the x-axis. Okay, so here's the positive x-axis. This angle that's made between the positive x-axis and the radius of the circle drawn out to where the object is at that moment. That angle there is going to be our angular position theta. To make things a little more complicated, we're always going to measure this angle in radians, and I'll tell you why in a second. But this angle is just always going to be measured in radians. It makes more sense for us to talk about it in terms of degrees. So sometimes in the beginning when we're practicing talking about angular position, I might, practice by saying, the object is at 45 degrees. And you could just picture, okay, this is approximately 45 degrees, and it gives you an idea that the object is right there. But really, when we do math, we're always going to need our angular position to be measured in radians. So just to help you convert, just because we're used to thinking in terms of degrees, a full circle has 360 degrees, and that's the same as 2 pi radians. So a radian is really just like, cutting up this, how many total, how far around you need to go to make a complete circle. Just chop that up into individual radians. There's 2 pi of those all the way around the circle. Just like I could take this circle and chop it up into individual angles, and if I cut it up into 360 pieces, each of those tiny little angles would be 1 degree. You could chop this up into tiny little pieces where each angle there is 1 radian, and then how many of those radians would there be in the full circle? There'd be 2 pi of them. So that's how we're going to describe angular position, and we'll get lots of practice with that. Now, you might wonder, why do we use radians instead of degrees? Because degrees are so much easier to understand. Well, the reason that we use radians is that, let's say I want to know the length of this arc here. So this is an arc, it's part of our circle, and let's say I want to know the length of that arc. This would represent if I had a car, and the car is driving in a circle. If the car started here, and it drove here, this length S is simply how far did it drive. How many meters is this length here? Okay, and if theta is measured in radians, then we have this really nice relationship that arc length, which I'm calling S, is just equal to r, the radius, times theta, where theta is my angle here. Then this equation only works when theta is in radians. If theta is in degrees, this does not work. Okay, so when theta is in radians, this equation allows us to get the length, which would be measured in meters, of this arc. And now let me just point out something that we're going to find a lot whenever we use radians. In this equation, S is a length, it's measured in meters. R is the radius, it's also measured in meters. And theta is this angle measured in radians. So you might think that this equation, the units don't work out because on this side I have meters and on this side I have meters and radians. So why are there no radians on this side? Well, radians is one of the few units that it can appear and disappear, and we don't care. We don't have to keep track of it and make sure that the equation is dimensionally consistent or it has the right units or the right dimensions. I have meters on this side, I have meters on this side. That's important to get the same units like that. Whether we or not we have radians, we don't worry about radians. Okay, so never try to think the radians are missing on this side. What happened to the radians? We don't care if the radians go missing. And we'll see that a lot in our future equations. Another way to kind of describe position that might be useful sometimes is to talk about revolutions. So if we're talking about this car driving in a circle, it might be useful for me to know how many revolutions the car has made. Okay, so a revolution is simply one full trip around the circle. And it's nice to kind of relate revolutions to the total arc length. If you drove around this circle once, if you made one revolution, we can think about how far did you travel in terms of meters, and how could I calculate that? And how far did you travel in terms of radians? How many radians did you drive through if you make a full circle? So think about that for a second. Well, one revolution would mean that theta is equal to 2 pi because we've gone all the way around the circle, and in one circle there's 2 pi radians. And our arc length, that would just be the entire circumference of the circle. Well, we know the formula for the circumference of a circle is 2 pi r. Or I could use this relationship here and say if theta was equal to 2 pi, then the total s, if I went all the way around the circle, my total arc length would be r times 2 pi, or just 2 pi r. Okay, so you can kind of see how having theta in radians makes this statement true and easy to understand. So let's just practice. Take a second, think through this, try to choose an answer. Now, I'm giving you answers here in degrees, and we'll practice converting between degrees and radians in a little bit, but take some time to try to figure this one out. Okay, so the hour hand is pointing straight up. Our angular position is always measured with respect to the horizontal. So I'm kind of looking at the angle between the horizontal and the straight up position because that's when it's midnight. Midnight is 12 o'clock. So that would be 90 degrees between the horizontal and that vertical position when the hour hand is pointing at 12. So 90 degrees, which would also be 2 pi radians.